Hey, it's Joel. We're in Frankfurt, Germany for Formnext, and we're going to be printing hot. How hot, Brandon?
Up to 500 degrees Celsius.
A big thanks to KiwiCo for sponsoring this episode. There you are. Welcome back. We're at Formnext in Germany. This is Brandon at Essentium. Hey, man.
Hey, how's it going, Joel?
It's going great. One of the things that I talk about on the show is materials that we could print typically below 300 Celsius. PLA and ABS and PETG and ASA, those sort of things. But we're at Essentium, and you specialize in things that go way above 300 C.
Way above.
So why don't we talk to the audience and give them a peek into these industrial, exotic materials that most people don't know about, don't extrude?
Yeah, let's talk about it. Okay, so everyone's familiar with PLA, ABS, PETG. You know, these are low temperature prototyping materials. They're good for everyday use kind of stuff. What we specialize in as a company is going beyond that. Higher temperature, higher performance, better chemical resistance. And that's when we get into really exotic stuff like PEEK, PEC, Ultem, PPS. These materials, most people have never really experienced these because they do extrude well beyond 300 degrees Celsius.
Yeah, that's
so
right.
Your desktop printer is probably not going to be doing it anytime soon unless you heavily modify it. We make some printers that specialize in it, and there's a lot of other printers that are starting to do these high temperature polymers, but industry's really interested in these because they have those really outstanding properties when you get into the kind of the exotic needs of the industrial sector.
I like these exotic materials because what I've heard is that typically these can be replacements for parts that are metallic, right?
Yes, yeah. They even sound metallic sometimes. Watch this.
Okay. That sounds like metal. That
Yes, it does.
sounds like metal, but this
Yep.
is not metal, right?
It's not. This is PPS, polyphenylene sulfide, with a carbon fiber reinforcement in it. So
Carbon.
it sounds like metal, but it is indeed plastic.
Okay, but it is. But what gives it that metallic ting? What makes that sound in that material?
It's really the chemical makeup. That's what starts this all off, because this is a semi-crystalline polymer, and that with the carbon fiber in there makes it a really high modulus. It's hard, it's durable, and it sounds like metal when you drop it.
Is that what gives metal its metallic sound? Is the high modulus?
Yeah, metals actually are crystalline themselves, but they have, you know, the chemical bonds in there are really stiff and strong, so that's why they sound all high-pitched and ringy.
Oh, okay. That makes a lot of
modulus.
sense. I
Yeah.
didn't even think about that. So it's PPS, polyphenyl sulfate?
Close.
Sulf.
Very close.
What'd I say?
Polyphenylene sulfide.
Phenylene sulfide.
Yep.
Polyphenylene sulfide.
It's a mouthful.
It is a mouthful, but it's got CF, meaning carbon fiber, chopped carbon fiber,
That's
which is
right.
going to give it stiffness, right?
Yeah, stiffness.
Without the CF, then does this have more bend to it?
It does, yeah. So if it didn't have the carbon fiber in there, it'd be a little bit more ductile. You can actually take filament without it and tie it into a knot.
What?
But the really cool thing, the really cool thing about this material, and with carbon fiber reinforced semi-crystalline polymers, is actually the outstanding benefits you get from putting that carbon fiber in there for chemical resistance and also for temperature performance. So here's the thing, we're gonna go back and talk about the chemistry a little bit of semi-crystalline and amorphous polymers.
The chemistry.
Chemistry.
The chemistry.
PLA, semi-crystalline polymer, ABS, amorphous. These are two different classes of polymers that we have in the thermoplastics category. So amorphous polymers, basically this just means that if you were to zoom in at the molecular level and look at those polymer chains, they're just random, all over the place, like spaghetti noodles.
So an amorphous polymer is something that's just like a soup of stuff.
Yep.
No soup for you.
At the
And-
molecular level.
Exactly.
Okay.
And it has this property called TG, a glass transition temperature.
That's right. Okay.
Yep.
I know that term.
Yeah. Okay, so with amorphous materials, as soon as you go above that TG, those polymer chains, they start to wiggle a lot. And then they can start to move and shift around and flow. So ABS has a TG of like 90 degrees Celsius.
Right.
So you go above that TG and all of a sudden, and it starts to lose all of its mechanical properties.
Because everything is kind of wiggling.
That's right.
Then it no longer has the rigidity and can't with.
Yep.
That makes so much sense.
All right, get ready to be mind blown though, all right? PPS has the exact same TG.
As
90,
Really?
exactly, yes.
Wait a minute. But this is.
It doesn't make sense, right?
This
Okay,
is
so here's
really
the thing.
stiff.
When you get to semi-crystalline materials, no longer when you zoom in on them are they all wiggly and weird and amorphous and have no structure to them. The polymer chains, as it cools down from the melt, they stack up into little crystals. So the entire thing in there, if you were to zoom in and look at it, has these regions that are crystalline. They look like little spheres. They're called spherulites, actually.
Spherulites.
Spherulites.
That's a great term.
Yeah.
And these are little areas in a semi-crystalline structure where the
So you got crystalline
Everything is-
regions and then
the molecules of-
amorphous regions on the outside, and it's like they packed all in together in this structure.
It's the meatballs and the spaghetti.
That's right. Yeah. Okay, so
Okay.
some materials are low crystallinity and some are high.
Meaning
so
the size of the meatballs.
the size and the number of, like
Ah.
the proportion, the fraction of how many in that polymer structure are actually crystallized. All right, so PLA, when you print it and it cools, it's actually almost amorphous. There's very, very little crystallinity in that PLA polymer, but it is semi-crystalline. And you've heard of people annealing it, right?
That's right.
So they're actually heating it up in order to grow those crystals bigger and increase the amount of the crystalline regions in that polymer. It gives
Oh.
it better temperature performance, better chemical resistance, better overall properties in general.
So I've annealed PLAs before, and I always thought it had to do, heating it higher meant you were lining up polymer chains.
That's exactly what you're doing. Yeah, you're lining them up into the crystalline regions.
I see,
Yeah.
I see. Oh.
Yeah. Now, PLA,
Okay.
even after you anneal it, it doesn't have that high of crystallinity.
Right.
Something like PPS, though, has a lot of crystallinity. So from a fraction standpoint, we're talking like between 25 and 50% crystallinity in the polymer, depending on how annealed it is. And that's what gives it really incredible chemical resistance, temperature performance, and overall that metallic sound to it.
Chemical resistance, though, meaning that PLA, a lot of times, chemical compounds could degrade the material. With PPS, though, so that's just not the case, or
That's
is it
right.
just less?
All right, so that's when we get into the chemistry.
Yeah.
So when we talk about chemical resistance, a lot of it has to do with, yes, whether it's semi-crystalline or amorphous. So by a general rule, semi-crystalline materials have better chemical resistance because those chains, when they pack up like that, it's actually much harder for solvents to get in there, to diffuse in and cause them to come apart. The chemical structure and that crystallinity really likes being a crystal.
We are the crystal gems!
It doesn't want to dissolve.
Is that described as a density?
Yeah, density, but it's also like the thermodynamics actually. Those crystalline regions are thermodynamically stable. They don't want to go apart unless you heat them up beyond their melting point. It's
Not the glass transition, but the melting point.
Yeah. So semi-crystalline materials like PEEK and PPS, they'll go past their glass transition temperature, but they can keep on going beyond that, and then you go to their melting point, and as soon as you hit the melting point, that's when they start to fall apart because those crystalline chains, it's actually melting like an ice cube.
I'm melting!
Now, when we talk about chemical resistance, it's not just about whether it's amorphous or semi-crystalline. It also has to do with the actual atoms and molecules that make up that polymer chain. Because some attachments, those chemical groups, when they link together, some are stronger than others. So PLA, not very chemically resistant because the actual bonds between those molecules are not super strong. They can be attacked by acids and bases and solvents. When you get into these superpolymers, these really high temperature things,
The bonds are stronger.
much stronger, much stronger.
So the chemical resistance actually has to do with the bonds at a molecular level.
That's right, yeah.
KiwiCo inspires kids to see themselves as makers, offering monthly crates that expose kids to concepts in STEAM. That's science, technology, engineering, arts, and math. Each crate that KiwiCo offers is designed by experts, but more importantly, it's tested by kids. KiwiCo is offering 9 different subscription lines, each catering to a different age group. Plus, these crates in those lines can be shipped to more than 40 countries. The crates themselves are self-contained and include everything you need in order to build the projects inside. This means you won't have to leave the house in the middle of a project to run to the local hardware store. All crates include kid-friendly instructions, and when you open the crate, you're gonna see that all parts are packaged incredibly carefully. KiwiCo crates are going to be an incredible option for holiday gifts because they're going to teach kids to build a gift. Build a memory, build a tradition. Right now, you can head to my link, kiwico.com/3D printing nerd. That's gonna get you 50% off your first month's crate. And that's any of the lines. 50% off, kiwico.com/3D printing nerd. 50% off your first month's crate, and just in time for the holidays. A big thanks to KiwiCo for sponsoring this episode, and now, right back to it.
So when we talk, people think about PEEK, right?
Yeah,
Super
which
chemically resistant.
PEEK is this one, right?
Yep.
Okay.
So semi-crystalline material, it's crystallized, and actually a cool way to tell about most semi-crystalline or amorphous materials, if you look at the unpigmented, just raw polymer, if it's opaque, it's probably semi-crystalline. if it's somewhat transparent, it's probably amorphous.
Well, I've noticed when annealing PLAs, they become more opaque.
Yep.
And that because things line up and it becomes more semi-crystalline.
Those spherulites grow and they actually scatter light. The light just bounces around, so it's no longer clear. The light doesn't just go straight through.
Oh.
Yeah, so
Okay, that's cool.
PMMA, glasses, polycarbonate, those are all amorphous. The light goes straight through it. There's no crystalline regions to scatter the light.
Huh.
Yeah. Okay, so we're talking about chemical resistance, and with PEEK and with PPS, because those polymer chains are really, really strong and the crystalline regions grow really quickly, those have a lot of stability against chemical attack in those polymer chains. So PPS actually is really, really strong because it's just a phenyl ring, like aromatic group, and sulfur over and over and over again. And that's a really, really stable chemical structure.
It's just that,
yeah,
and then that, and then more, and
over
more,
and over and over again.
more.
And it stacks up into these really, really orderly, neat crystalline regions and strong. And the thing is with that, there's no known solvents for PPS below 200 degrees Celsius. So if you ask me what is PPS's chemical resistance, my answer is yes.
What? So wait, you could have a container made of PPS and put like a hydrochloric acid in it, and it would just shrug and be okay with it,
mixed with acetone and chloroform and methyl ethyl ketone. It's just going to blink it and be like, yeah, no problem.
Unless you heat it up over 200 C, because then it's changing the chemical structures.
Yeah, you're starting to get to the point where the molecules are vibrating a little bit more. There's a little bit more space, and then the solvent get in there.
And it's susceptible.
Yeah.
Oh.
Yep.
That makes so much. That is cool. Like I understood why this is an engineering grade material. I knew that it was chemically resistant, but I didn't understand why.
Yep.
And that makes a lot of sense. I don't know. This is just cool.
All right.
This is so cool.
Let's keep going.
Yeah. What else you got?
Ultem.
Ultem.
This is Ultem.
Oh, we saw that at in Chicago.
That's right. Yeah. Okay. So PEI Ultem 985. Everyone's really familiar with this material in the industrial segment, especially aerospace, because it has really good flammability behavior.
Oh, it won't catch fire.
That's right.
Okay.
And so if you're in an airplane, there's actually these regulations that the FAA has, FAR 25853, where they take these little coupons,
it off the top of your head.
Boom, and they burn them, and they make sure that it doesn't propagate or continue flaming off and catching on fire. They don't want it to put out a lot of smoke or toxic chemicals, and this material has outstanding resistance against that.
So that's not only aerospace, but I would imagine space travel and,
that's right.
and that sort of thing, because they need that sort of performance.
Yeah. This material is really popular for like aircraft cabin interiors, but if you go outside the aircraft and you have components that are on like the landing gear or in the bottom of the plane, and it's going to get exposed to like hydraulic fluids or chemicals like de-icing fluids, that's something where this is actually not going to stand up very well, because this is an amorphous polymer. This is actually a polymer blend, so they've kind of blended in two different amorphous polymers.
Well, if I'm looking at this molecule, then where PPS is simple and the bonds are strong, there's a lot of opportunity here for the strength of the bonds to not be as strong?
Well, it's still a strong backbone, but it's actually a little bit more chaotic and random, so it's harder for those polymer chains to like find their nearest neighbor and join up. It's so disordered. Okay. There's these bulky side groups in here. If you take any polymer and you like hang a giant molecule off the side of it, it's really hard for it to like find its friend and like link arms and like get into a crystalline region. So that's actually, it's got...
They suck at Red Rover,
That's right, yeah. So it's really stiff in the backbone, but it doesn't order very nicely, but this has something of very, very high TG. So everyone thinks of Ultem as being this really high performance polymer. It does have a high glass transition temperature, up to about 174 degrees Celsius.
Oh, okay.
Yep. So it will withstand very high temperatures. As soon as you get up to that TG though, it'll and it's done. But most of the time you don't need to go much above like 150, 160 degrees Celsius.
So then Ultem PEI, the applications for that are going to be things that need to withstand flammability,
That's
like
right.
you were saying, but not in areas where temperature could rise. So not engine
Beyond
bays,
that, yeah.
not stuff like that. But
and chemical resistance. That's the other thing. If you had any kind of chemical or solvent, this isn't going to do very well. Now that's actually why we got into PEC. Enter PEC. So
polyethyl ketone.
Yeah, you got it. Yes. Okay, so everyone's familiar with PEEK. polyether ketone.
Yes.
We're talking about PEC. So it's it's in the same family of polyaryl ether ketones.
Polyaryl ether ketone.
Aryl ether ketones.
Aryl?
Yeah, aryl.
Aryl, what does that mean?
So aryl is that little like ring group right there. It's the
Okay.
benzene ring with the two things hanging off the side. That's an aryl group. So basically we're just saying.
Oh, so in PPS, that's a benzene ring as well?
Yeah, it's an aryl salt phone.
Oh, and so these are similar in that.
Similar, yeah. So a lot of the high performance materials have that backbone with an aromatic group. We call it aromatic because it has a ring on it. Organic chemistry. We won't get that
I was
deep.
like, aromatic, it smells good?
Okay, so if you take those groups and you link them together, so PEC is ether ketone. So we've got two ether groups. We've got an ether group here and an ether group here, and then a ketone group there, the double bonded oxygen.
Oh, those
right
two
there.
lines mean double bonded.
Yep.
Okay.
And that's the ketone group. Now on PEC, it's polyether ketone. So we've got an ether group and then a ketone and a ketone.
Oh, okay.
Yep. So you got two of them.
It's similar.
Very similar.
But,
it's
okay.
very nuanced. Now the difference here is that actually there's two ways of doing this. You can either put this group here or you can put it on the side up here. So our good friends at Arkema who make Kepstan resin, they've actually copolymerized it. And by changing the ratio of that, they can actually tune it so that it's either amorphous or semi-crystalline.
And it's able to link up
Yep.
and be either amorphous or semi-crystalline. Or
Yeah.
they can design how amorphous or semi-crystalline it is.
Exactly. They're really actually designing the rate of crystallization. So as you melt it and then it cools down, this grade actually takes like 15 to 20 minutes for it to crystallize. So in normal printing processes, it's almost always going to come out amorphous, pseudo-amorphous, they say actually. You can anneal it. So this is like PLA. This is almost exactly like PLA because you could take this and put it into an oven and increase its crystallinity a little bit. But one of the really cool things about that is that as a printing material, this prints really nicely. It's like PLA,
It's
but
like PLA.
if you just bumped all the temperatures up by like 200 degrees Celsius,
Yeah, turn up the heat.
it's like printing PLA, seriously.
It's the engineer's PLA.
Exactly.
That is amazing.
And one of the reasons why people actually struggle to print with PEC, PEC, amazing material, outstanding chemical resistance, really expensive, but it crystallizes. And when things crystallize, they actually shrink a lot. So the polymer chains are ordering up really nicely and it goes and it shrinks in. So it's really, really hard to make big PEC parts that are really flat and dimensionally accurate.
Oh.
And that's one of the main things
Because
that
in
people
shrinking, then they'll pull up from print beds.
So you have to be very good at printing and slicing and understanding how to work with these materials in order to get them to come out really flat and dimensionally tolerant. But with PEC, it's like PLA. So as it cools, it only comes in a little tiny bit.
Really?
And it doesn't really, look at this part. Look how flat that is for how big it is.
So this is a PEC part.
PEC part.
And this
Yep.
is,
dead flat.
that's
And
flat.
we didn't even we printed it the first time, didn't even have to optimize anything. It was just dead flat, perfect. So this material is really, really incredible to work with if you need those high temperature, high performance properties, excellent burn behavior, flammability behavior,
Chemical resistance?
chemical resistance, yeah.
Oh.
So it has better chemical resistance than this material, Altem,
But not as good as.
but not as good as this and this. PEC
so
and-
where would
PEC
we
and
see
PPS.
PEC parts?
Okay, so if you're in aircraft cabin interiors, Altem.
Altem, okay.
Outside of the aircraft interior, that's when you're going to go with PEC.
Oh,
If you're making a plane. So
Okay.
if you have, resistance to hydraulic fluids, de-icing fluids, light duty solvents that are going to, be painted on, this actually has really good resistance to that because it has a little tiny bit of crystallinity. We're not talking like 30, 40%. It's like 2, 3, 4, 5%.
but enough.
But enough to actually link the polymer chains enough that they're not going to do environmental stress cracking or just like falling into a soup like this does.
Okay. I've heard of this, and I mean, I've talked before about PEC and PEEK and these high temperature materials, but I've never heard it referenced as a PLA
Yeah.
with 200 degrees of, a 200 degree difference between
bump
this and
everything
PLA.
up.
Just bump everything up.
Yeah.
But that's amazing to think about because this means that everything that people are doing in their garage or maker space or school, that they're modeling things in a specific way or slicing in a specific way to make sure things adhere to the bed and don't fold up and don't shrink too much. All of that is then applicable to working with PEC.
Yep.
They just have to adjust their temperatures and maybe just get used to it.
Same
a little
exact
bit.
mindset, just like use a little bit different bed temperature, bed adhesive, and higher everything on the temperatures, and you can pretty much print any PLA part you would with PEC.
But that's it. I mean, that's literally it.
Yeah.
Wow.
You did ask about 3 good things about a material, so we've
yeah.
talked about a lot of good things.
Yeah.
You know, why would you not want to use a material? We can talk about that briefly. So
okay.
we did say for PEEK, it's actually really hard to make big, complex parts with
That's right.
dimensional accuracy, so you really need to know what you're doing in order to get that to work well. So,
so it is possible.
it is possible. You just have to work really hard to get it.
I
and
see.
you may have to anneal it and print it many times to kind of get the shape and account for that shrinkage. So,
Or you could go to PEC.
or you could go to PEC. Now, the reason why you may not want to use PEC is it is expensive, and also it's not going to have as much chemical resistance as PEEK does. So it's a trade-off. You can't
Right.
have everything. Now, for PPS, amazing temperature performance. It's actually called also the poor man's PEEK. So it's like 1/4 of the price of PEEK.
Okay, PEEK
Yeah.
is how much per kilogram?
Usually in the marketplace between $600 and $800 a kilogram.
Oh, so this is more like $150, $200 a kilogram?
175.
Oh,
Yep.
right there.
Yep.
If someone, though, at home didn't have a massive machine, but wanted to experiment, like this is legit a material they might be able to get away with
Pretty
printing?
close, yeah. So it extrudes at about 320, 330 degrees Celsius. So if
That's
you,
within some extended ranges
yeah,
if people
have
upgrade
been
the-
printing on Altimakers. If you kind of
Really?
like override it and get it a little bit above its offset temperature, you can get
Yeah.
it to print on an Altimaker. You should anneal it afterwards though. So when we print it, we're actually elevating the chamber temperature quite high so that we really get that high degree of crystallinity.
And then if it shrinks at all, it's a uniform
Exactly,
shrink.
exactly.
Oh, so if you're printing this in an Ultimaker, you do run the risk of having, yeah.
Yeah.
Okay.
Yep.
Oh, that's
Now,
interesting.
There's a lot of carbon fiber in there, and that helps because it really stiffens it up and stabilizes the polymer. So
Yeah.
if you did anneal it, it's not going to warp as much as, say, PEC if you tried to anneal that. But this material, it is going to work much better if you have a heated build volume. It's not going to shrink or have dimensional distortion as much as if you were to print it on an Altimaker.
Okay, well then, but if, for annealing though, what is the annealing temp for PPS?
Right
Is
ar-
that the glass temp? Or
Yeah,
is-
so you have to go above the glass transition temperature.
but below melting.
But below melting, yeah. So we're going to
okay.
generally anneal it around 140 to 150 degrees Celsius.
Oh, okay.
Yeah, it's not too bad. Now, another thing about this material, it does
Yeah.
sound really high modulus, and it's really stiff. So one reason why you may not want to use this, if you have really thin walls or things that need to be bent a lot or have a lot of toughness, like you're going to whack it,
Yeah.
this may not be the best material for that. The carbon fiber makes it really, really stiff, but not as impact resistant.
Is
or
it brittle then at that point?
Yeah, I'd say it's brittle.
Okay.
It's like metals and ceramics, the stiffer they get, the more brittle they are.
Right, that makes sense.
But we love it for tooling. So we actually print
tooling?
injection mold tools out of this material.
Oh, okay.
Yeah, we print the cavities that you would put on an injection molding machine out of this material. We'll print it, you can do conformal cooling, you can get in there with a CNC mill and kind of finish the surface up, and it's a replacement for aluminum in that case.
Oh,
Yeah.
Which means the costs for bringing up your forms then.
Way lower.
Oh, that's cool.
And way faster. That's the key, is quick turn tooling. You can be printing this and overnight have your injection mold tool ready to go and you can start shooting parts on it. We have customers that are doing this right now with overmolding of cables. And they're trying out these new cable connectors and it takes them a long time to get just the right fit for an aluminum tool, but they're iterating and prototyping with this material so that they can shoot a tough polymer over top of their cable.
Never would have thought.
Yeah.
That's cool. Well, this has been quite a data dump,
Yeah.
but I understood a lot of it.
Yeah.
Like, you have a great way of explaining things, and it's really cool to see how much of that experience on the consumer side really lends itself to the beginnings of working with these engineering grade materials. Is there more information where people can go to learn about you or what you're doing on the material side of things?
Absolutely. So if you go to our website, we actually have a whole informational series. We have webinars, we've got white papers, we've got a lot of information on our materials on the TDSs, the technical data sheets that you can get on our materials page. So you can learn more about it there too.
Just available for download.
Exactly, yeah.
Oh, okay.
I've actually got a lot of YouTube videos that we go in and we do deep dives on these materials. We talk about the chemical structure, the history, like who invented it, and where did it come from? So that's all online too.
Well, we'll put a link down in the description. And obviously, for everybody out there who's watching, Brandon's awesome. But if he missed something or you have more questions, leave those in the comments and maybe we bring Brandon back for round 2. What do you say?
Let's do it.
If you made it this far, you're awesome. Don't forget to hug each other more, fight for a cause you believe in. And as always, I'm going to offer them a high five. Ready?
All right.
High five.
High five.
Nailed it.